woke up. Fuck. So tired. I did not meet Bali yesterday, bro. So Bali said we can meet on. Fuck. What's up, guys? What's up? What's up? Oh, shit. What's the plan for today? Same plan like yesterday. Do deliveries, eat, sleep, deliveries, eat, sleep. Fucking Matrix, bro, Matrix. What you guys gonna do? What's your plan? Anything interesting? Anything? And Rust. Come on, guys, click the like button so the live goes to more people. Oh, shit. I want something sweet. Maybe I should get a donut. Or I need yogurt. Just wanted to ask about your business from last year. That's no, bro, no. It was not profitable, so we stopped it. Not bad terms. It's mutual. Broke up. Hold on. Yeah. Donut. Donut. I want Boston cream from Tim Hortons. How many deliveries do I have today? I still haven't gotten my paycheck. It's been 4 days. I don't know why he's delaying it. What about the Bango business? What happened with it? I did not get the orders, bro. I did not get the orders. Fuck, he's not gonna pay it. Summer is over now. 2025 is gonna over. What did I do in 2025? Nothing. So bad. At least in 2024 I tried something with Indian Shackles. In 2025 I did nothing. Didn't even try anything. Didn't make money. Did not travel much. It's a waste. What's up, guys? What's up? Someone press the button, yaar. Yeah, someone pressed it. What up, guys? What up? Let's listen to some podcast or something. Why it's not playing anything? What the fuck is happening?
From your perspective, his time is slowing down. At the very instant when he should cross the event horizon, the point beyond which not even light can escape, he and his rocket ship do not disappear. Instead, they seem to stop. You can never see anything enter a black hole. Imagine you trap your nemesis in a rocket ship and blast him off towards a black hole. He looks back at you, shaking his fist at a constant rate. As he zooms in, gravity gets stronger, so you'd expect him to speed up. But that is not what you see. Instead, the rocket ship appears to be slowing down. Not only that, he also appears to be shaking his fist slower and slower. That's because, from your perspective, his time is slowing down. At the very instant when he should cross the event horizon, the point beyond which not even light can escape, he and his rocket ship do not disappear. Instead, they seem to stop, frozen in time. The light from the spaceship gets dimmer and redder until it completely fades from view. This is how any object would look crossing the event horizon. Light is still coming from the point where he crossed, it's just too redshifted to see. But if you could see that light, then in theory you would see everything that has ever fallen into the black hole frozen on its horizon, including the star that formed it. But in practice, As photons are emitted at discrete intervals, so there will be a last photon emitted outside the horizon, and therefore these images will fade after some time. This is just one of the strange results that comes out of the general theory of relativity, our current best theory of gravity. The first solution of Einstein's equations predicted not only black holes, but also their opposite, white holes. It also implied the existence of parallel universes and even possibly a way to travel between them. This is a video about the real science of black holes, white holes, and wormholes.
White holes?
The general theory of relativity arose at least in part due to a fundamental flaw in Newtonian gravity. In the 1600s, Isaac Newton contemplated how an apple falls to the ground, how the moon orbits the Earth and Earth orbits the sun, and he concluded that every object with mass must attract every other. But Newton was troubled by his own theory. How could masses separated by such vast distances apply a force on each other? He wrote that one body may act upon another at a distance through a vacuum without the mediation of anything else is to me so great an absurdity that I believe no man who has a competent faculty of thinking could ever fall into it. One man who definitely had a competent faculty of thinking was Albert Einstein, and over 200 years later, he figured out how gravity is mediated. Bodies do not exert forces on each other directly. Instead, a mass like the sun curves the space-time in its immediate vicinity. This then curves the space-time around it, and so on all the way to the Earth. So the Earth orbits the sun because the space-time Earth is passing through is curved. Masses are affected by the local curvature of space-time, so no action at a distance is required. Mathematically, this is described by Einstein's field equations. Can you write down the Einstein field equation?
This was the result of Einstein's decade of hard work after special relativity. And essentially what we've got in the field equations, on one side it says, tell me about the distribution of matter and energy. The other side tells you what the resultant curvature of space-time is from that distribution of matter and energy. And it's a single line. It looks like, oh, this is a simple equation, right? But it's not really one equation. It's a family of equations. And to make life more difficult, they are coupled equations, so they depend upon each other. And they are differential equations, so it means that there are integrals that have to be done, blah, blah. So there's a whole bunch of steps that you need to do to solve the field equations.
To see what a solution to these equations would look like, we need a tool to understand space-time. So imagine you're floating around in empty space. A flash of light goes off above your head and spreads out in all directions. Now, your entire future, anything that can and will ever happen to you, will occur within this bubble, because the only way to get out of it would be to travel faster than light. In 2 dimensions, this bubble is just a growing circle. If we allow time to run up the screen and take snapshots at regular intervals, then this light bubble traces out a cone, your future light cone. By convention, the axes are scaled so that light rays always travel at 45 degrees. This cone reveals the only region of space-time that you can ever hope to explore and influence. Now imagine that instead of a flash of light above your head, those photons were actually traveling in from all corners of the universe, and they met at that instant and then continued traveling on in their separate directions. Well, in that case, then into the past, these photons also reveal a light cone, your past light cone. Only events that happened inside this cone could have affected you up to the present moment. We can simplify this diagram even further by plotting just one spatial and one time dimension. This is the space-time diagram of empty space. If you want to measure how far apart 2 events are in space-time, you use something called the space-time interval. The interval squared is equal to minus dt squared plus dx squared. Since space-time is flat, the geometry is the same everywhere, and so this formula holds throughout the entire diagram, which makes it really easy to measure the separation between any 2 events. But around a mass, space-time is curved, and therefore you need to modify the equation to take into account the geometry. This is what solutions to Einstein's equations are like. They tell you how space-time curves and how to measure the separation between 2 events in that curved geometry. Einstein published his equations in 1915 during the First World War, but he couldn't find an exact solution.
What
Luckily, a
up,
copy of his
guys?
paper made
What
its way to the
up?
Eastern Front, where Germany was fighting Russia.
What up?
Stationed there was one of the best astrophysicists of the time,
What's
Carl
up?
Schwarzschild. Despite being 41 years old, he had volunteered to calculate artillery trajectories for the German army. At least until a greater challenge caught his attention: how to solve Einstein's field equations. Schwarzschild did the standard physicist thing and imagined the simplest possible scenario: an eternal static universe with nothing in it except a single spherically symmetric point mass. This mass was electrically neutral and not rotating. Since this was the only feature of his universe, he measured everything using spherical coordinates relative to the center of this mass. So r is the radius, and theta and phi give the angles. For his time coordinate, he chose time as being measured by someone far away from the mass, where spacetime is essentially flat. Using this approach, Schwarzschild found the first non-trivial solution to Einstein's equations, which nowadays we write like this. This Schwarzschild metric describes how spacetime curves outside of the mass. It's pretty simple and makes intuitive sense. Far away from the mass, spacetime is nearly flat, but as you get closer and closer to it, spacetime becomes more and more curved, it attracts objects in, and time runs slower. Schwarzschild sent his solution to Einstein, concluding with, "The war treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas." Einstein replied, "I have read your paper with the utmost interest. I had not expected that one could formulate the exact solution to the problem in such a simple way." But what seemed at first quite simple soon became more complicated. Shortly after Schwarzschild's solution, what's physically happening. This is what's called a singularity. Maybe that point could be excused because it's in the middle of this, but there's another problem spot outside of it. At a special distance from the center, known as the Schwarzschild radius, this term blows up. So there is a second singularity. What is going on here? Well, at the Schwarzschild radius, the spacetime curvature becomes so steep that the escape velocity, the speed that anything would need to leave there, is the speed of light. And that would mean that inside the Schwarzschild radius, nothing, not even light, would be able to escape. So you'd have this dark object that swallows up matter and light, a black hole, if you will. But most scientists doubted that such an object could exist because it would require a lot of mass to collapse down into a tiny space. How could that possibly ever happen? Astronomers at the time were studying what happens at the end of a star's life. During its lifetime, the inward force of gravity is balanced by the outward radiation pressure created by the energy released through nuclear fusion. But when the fuel runs out, the radiation pressure drops. Gravity pulls all the star material inwards. But how far? Most astronomers believed some physical process would hold it up. And in 1926, Ralph Fowler came up with a possible mechanism. Pauli's exclusion principle states that fermions, like electrons, cannot occupy the same state. So as matter gets pushed closer and closer together, the electrons each occupy their own tiny volumes. But Heisenberg's uncertainty principle says that you can't know the position and momentum of a particle with absolute certainty. So as the particles become more and more constrained in space, the uncertainty in their momentum, and hence their velocity, must go up. So the more a star is compressed, the faster electrons will wiggle around, and that creates an outward pressure. This electron density pressure would prevent the
What up, guys? What up? Community center? No, bro, no, no, no. No community center. When do you meet up with friends and all? Yeah, when they are free. Like, all my friends are working 2 jobs, so it's hard to coordinate. They're all making so much money, except me. I'm, I'm hungry. I wanna sleep. I don't want to work. What movie should I watch today? I want to watch Nobody 2. Let's see if it's available online. I don't think it's online. Nobody. Nobody 2 is not. I know you don't like working, but do it for a change. Yeah, you're hiring at my friend's place, but I don't want to. Hello, Marriage was good, decent. It was good movie. But like, that's so they fell in love in like 3 months. Mm, mm, mm. Be honest, are you fed up with living in the car? Of course, bro. I'm bored. I'm super bored. I need to find something else. Life is not interesting. Mm, mm, mm. What up, guys? What up? Then make changes. Join with your friends even if you don't like. Force a change. Ah, yeah. What to do? Let's go out. Let's go out and pick the orders. I'm in Vancouver, bro. I'm in Vancouver. I'm gonna pick up the orders. See, it's hard. See, it's so sunny.
Do you want us to print another mail label, or is this okay? Like, it's just in the bag together.
Both are same?
Both the same.
Okay.
Both the same.
Yeah.
Yeah, so the address is on both of them, but they're both the same person.
Okay. Yeah. Got it. Thank you.
Thank you.
What up, guys? What up? What is fit life, bro? I don't know what you mean. Explain. What is fit life? Lads. I don't know what you're talking about, bro. See, I'm seeing those trucks a lot. It's the electric vans, you know. I'm seeing it a lot nowadays. Someone is selling it a lot. It's electric, right? Okay. What to do now? What to do? What to do? What to do? Pick the first order. What Fed does? I don't know, bro. What is Fed? What is Fed life? So I think I'll go and pick up my Tiffin service. The event you went to, one of the older folks sent a picture of you at the beginner poker. What? Sent a picture of you at the beginner poker. What do you mean? I don't know. What is poker? I don't even know how to play poker, bro. I don't even know what is poker. Fetish. What is fetish? I'm bad at English, bro. To do. Should I go to my? Should I go and eat? Mm-mm-mm. Let's go eat. I'm hungry. Mm-mm-mm. What? Let's go. What up, guys? What up? Fuck. Fuck. So stupid. I should have gone the other way. Is it veg food today? Yeah, bro, yeah. Every day is vegetarian, bro. I accidentally paid for the vegetarian food. So I'm eating vegetarian food every day. Maybe next month I'll pay for the non-veg. Non-veg is a bit expensive. Yeah. Punjabi food, he is sick of Tamil. I couldn't find any Tamil tiffin service, bro. So Punjabi ones are the ones I could find on Fraser. I don't want to come back. I'm waiting for one more order, but like he hasn't placed the order, so I don't want to come back here. Yeah, I waited 20 minutes. Please don't order once I get there. And I have to come back here. And then I have to go back. It's a waste of gas, waste of time. What up, guys? What are you guys doing? What should I do? You guys have any idea? I miss my adventure. I want to have some adventure, some fun. Any ideas? See, I don't even know how to whistle. so long since I went for hiking. I used to go for a hike a lot, right? Last year. This year I haven't gone. I only gone to Gross Grind. Maybe I'll go this Sunday. I miss the camera shy girl, Bali. Yeah, me too, bro. Me too. I want to find more friends, more female friends. I only have Bali. I need more. I don't know where to find. Your 2025 has been so boring, lol. Yeah, it is boring. So boring. But I hope 2026 is gonna be a blast. Let's hope for the best. Money is the problem, you know. If I can have like 40k, 50k. I thought it would be easy to make like 40, 50k, but like it's not. Apparently, it's too hard. Too much effort. Too much. I'm gonna ask Snowgirl about you on her TikTok live. Is she going live? I don't know. I don't think she goes live anymore. And I don't care. You can ask whatever you want, bro. Don't tell me. I don't wanna talk about her. She's gone. She's no more. Okay. So please don't talk about the ones that I forgot. You have to move forward, bro. You have to make new friends, new people. You have to forget the past and move on. Plus, you don't even know her ID, huh? Exactly like me. That's how you do it. What up, guys? What up? What up? I want to go to Montreal. Should I go to Montreal? Do you guys remember that I got a ticket for using phone, distracted driving? So I filed. So the court date is next month. I don't know what to do. I don't have a lawyer. Do you guys know what to do? Anyone? Or maybe I'll pay the fine. I don't know. I want to go to Montreal, Quebec. Maybe I'll learn some French, which will help me in my PR. Well, I'll stay there for 6 months. They have DoorDash in Montreal, right? DoorDash, Uber Eats. They should have. So I could do the same thing there. Oh, nice bike. Ah, it's really nice. I think he built it himself. So nice. Until they speak French, no. Dude, I know. I want to learn French, bro. I know a little bit. I know Jatem, Jamapal, Kama Tapal, Kama Sava, Saba, Trebian, Silvo Play. That's all I know. They will make you pay a fine. Yeah. Shit. Susan needs to go to casino and put it all on. I don't even have money to gamble, bro. See, I got my paycheck and I paid off all my like last week's credit. Now I'm zero. Now I have to use the credit card. And next week I will get the paycheck. I have to pay off the credit. See, I'm in a fucking loop, doing the same fucking thing again and again. I have to break the loop. That's why I'm planning to sell Carol. So once I sell Carol, I like I'll have some cash, maybe. I don't know. I'm living paycheck to paycheck. Feed finder. What is feed finder? It sounds bad. What is feed finder? He's so slow. Oh my god. Excuse me. I'm so hungry. There's no demo dance. I can't get donuts. So, what's the latest movie you guys watched? I want to watch a movie. I talk to my parents every day, bro. I'm an Indian guy. We talk to our families every day. I want to break this loop. I'm in a fucking loop. You guys broke your loop, or you guys also still in the loop? Susan, can you give a home tour? I don't have a home, bro. I don't have a home. car tour, which is your home. Jack did not have. Dun, dun, dun. It's not a car, bro. It's Carol. Give respect, bro. It's so sunny today. Okay, let's go. Dun, 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 dun. My bad. First, I need to buy some milk. I need some calcium. So. Watermelons. I want to buy some watermelon. Maybe later. Or should I buy it today? Not today. Not today. Sunday. I can buy watermelon on Sunday. Because Sunday I don't have tiffin. So I can eat watermelon the whole day. I don't know what to buy. See, I want to buy this 4-liter one, but I don't have a fridge, so I don't know whether it will go bad. And it's so hot nowadays. What should I do? Should I buy the 4-liter one or the 1-liter one? 4-liter is cheaper, but I don't have a fridge. I can finish it in maybe 2 days. What should I do, guys? Yes, it will go bad. $8, $3 more. I want at least 2 liters. Should I buy the 4-liter one? I want to buy the 4-liter one. Because it's only $3 extra. I'm getting for $3. I'm getting 3 liters extra. I'll keep it under the under my mattress, or like I'll keep it somewhere cold. Okay. So I bought the fucking monitor. I don't know what I'm gonna do with this. It goes back by September 2nd. So I have like 10 days. Maybe I'll keep it in my friend's place. I don't know. Okay, let's go and get our fun. Wasting money? I'm not wasting money, bro. I need milk. I need protein. I need calcium. I'm not wasting money, okay? Anyway, I'm gonna buy you the 1 liter one, which is like $5. Instead, I bought this for $8, 4 liters. So even if I drink 2 liters and if I waste 2 liters, that's a pretty good value for money, right? Like I'm not losing anything if you think about that. Because 2 liters is $10. Okay, so I'm just only spending $8 for 2 liters. I don't think it will go bad tomorrow. So yeah. Thank you. Thanks. Bye, bro. If you're gonna keep it in your car rather than a fridge, it will go bad. So yeah, losing money. I will drink it, bro. I will drink 4 liters today. I don't have a location, bro. I don't stay at one place. Right now I'm in Kingsway. I'm right now I'm close to Hyderabadi Biryani House. I'm gonna eat and then I'm gonna move. So I keep moving, bro. My foot is here. Let's drink some milk. Let's see how it tastes. BC fresh milk. See? What the heck? Not bad. Okay, let's eat. And we gotta go pick up the orders. Oh, cauliflower! My favorite is here. Let's eat the rice. Looking like a whole gym bro with a drinking. I never went to gym in my life, bro. Oh, it's too hot. Now the heat quick. See, I don't even know what this is when I'm eating it. It's like bonda or something. I usually buy apple, 2 apples, but like today I spent more money on milk, so I didn't buy apples today. I'm at zero, bro. I'm at zero. I'm at zero in my career. No, it tastes like more Colombo. In Tamil, we used to call it more Colombo. They used to make it with curd, things like that. Let's open the cauliflower. So I have potato, cauliflower. This is good. And I have rotis, but I'll eat rotis in the evenings. To I'm done. I'll finish it later. AC, I need AC. It's too freaking hot. See, I like it so much I can't even fucking stop drinking it. I think I drank 1 liter by now. I only have like 3 more liters, which not a big deal. So what do you guys want to listen to? Science fiction. I cannot watch movies. What should I do, guys?
Quantum mechanics is the foundation of our understanding of the universe. To truly grasp quantum computing, we need to conquer the strangeness head on. In this video, we'll explore 3 key examples of quantum systems, each one peeling back the layers of quantum mechanics, and in doing so, bringing us closer to understanding quantum computing. As Richard Feynman once said, if you think you understand quantum mechanics, you don't understand quantum mechanics. But there's a problem with this.
Today's cutting-edge technologies, atomic clocks, quantum sensors, and quantum computers, aren't just built on quantum mechanics, they actively control and harness quantum states. In this video, we'll defy Feynman's warning and see how we turn quantum weirdness into something practical. First, let's take a look at a single electron. Associated with subatomic particles like electrons is a quantity known as spin. Spin is just a form of angular momentum, and it gets its name from the fact that it makes the electron behave almost like it's spinning like a top. Since when charged particles spin, they get magnetized, spin effectively makes electrons tiny little magnets. The spin of an electron can be in two possible states, either spin up or spin down. The direction of spin tells you about the direction of the magnetic field from the electron. Importantly though, when we measure the spin of the electron, it can only be either up or down. In other words, the spin of the electron is binary. If this electron spin were like a normal system that we study in classical physics, that would be the end of the story. However, quantum mechanics lets us do something interesting. When we find the allowed states of a quantum system, we do it by solving a differential equation known as the Schrödinger equation. Any physical state that we get from solving the Schrödinger equation is known as an eigenstate, and is an allowed state for our particle to be in. In this case, spin up and spin down are the eigenstates. But this is where it gets interesting. The eigenstates aren't the only allowed states. You can take two eigenstates and combine them together to make a new state, which is some bit eigenstate A and some bit eigenstate B. This new state is called a superposition. So there's another option that we didn't have access to in the classical setting. Our electron can either be spin up, spin down, or in a superposition of both spin up and spin down at the same time. This is one of the fundamental characteristics of a quantum bit or qubit. A switch, on the other hand, is a good classical representation of a scenario like this. A classical switch can be open or closed, but it can't be in a superposition of both. In general, it's possible for a classical system to be put into a state between two extremes. For example, a door can be open, closed, or somewhere in between. But the difference is that when you look at the door, i.e. when you measure it, you measure the door to be in that intermediate state. It doesn't collapse to be open or closed. In other words, the state of the door is definite the whole time. In contrast, if you have an electron in a superposition of spin up and spin down, when you measure that electron spin, you will measure either spin up or spin down, not the combination of both. We can represent the state of any spin-like quantum system, meaning a system with two allowed states, using something known as the Bloch sphere. The Bloch sphere is a three-dimensional visual representation of the superposition. Physically, the Bloch sphere represents a lot of ideas in a very compact notation. The radius of the Bloch sphere is the easiest thing. Every superposition state of our electron that combines spin up and spin down lies on the surface of this sphere. Spin up is along the plus z direction, and spin down is along the minus z direction. If you plot a state on the Bloch sphere, you'll notice a couple of important angles. The first of these angles is called theta, which is the angle that the point on the sphere makes with the z-axis. This angle basically tells us how much of a superposition we're in. For a theta angle of 0, the state is 100% spin up. For a theta angle of pi, or 180 degrees, the state is 100% spin down. For anywhere in between, for example, theta equals pi over 2 or 90 degrees, there are a bunch of different possible states that make a circle all the way around the sphere. This is where the second angle, phi, comes in. Phi is known as the phase. While it doesn't control the probability that you'll measure spin up or spin down in a single qubit, it allows for different qubits to interfere with one another in quantum algorithms. This is something that I'll talk about more in another video. Next, let's take a look at another physical system, atoms. If we zoom into a single hydrogen atom, we find more discrete states. In the case of the single electron, the states were spin. In the hydrogen atom, however, the states that we're going to look at are the orbital states of the single electron whizzing around the nucleus. There are some other differences as well. When we solve the Schrödinger equation for an atom, instead of getting two allowed states like we do for an electron, we get an infinite tower of states. If we have an atom in one of these states, we can transition to another by shining in a laser with a very specific color. Since the color of a laser is related to the energy of the photons of light in that laser beam, if we shine a laser on the atom, which has a color that corresponds to the energy difference between two states, the electron in our atom has a chance to absorb that photon and transition up to that state. For example, if we shine in a red laser, This corresponds to the transition between the n equals 2, or second, and n equals 3, third energy levels. If we shine in a blue laser, however, this corresponds to the n equals 2 to n equals 5 transition, raising our electron from n equals 2 to n equals 5. If we keep shining in these lasers, we can also do the reverse process called stimulated emission, where the incoming photon kicks the electron back down. Since shining a single laser color lets us focus on two specific states and ignore the others, we can draw a Bloch sphere just like we did for the electron spin. This time, instead of the states being spin up or spin down, they'll be the 2 and 5 electron states. Thus, in this case, our theoretical atom-based qubit states are the n equals 2 and n equals 5 states. Again, just like before with the electron spin, we can generate superpositions of multiple states. To do this, we shine in the laser for a shorter period of time. Specifically, if we want to make an even superposition of the n equals 2 and n equals 5 states, we first record the amount of time that it takes to promote the electron from n equals 2 to n equals 5. This time is known as a pi pulse duration, because it changes the angle theta on the Bloch sphere by the value pi, or 180 degrees. To put our qubit into an even superposition of 2 and 5, we apply a pi over 2 pulse. This is a laser pulse at the same frequency or color of the pi pulse, but for half the time. Not only can we create superpositions of two states in a single atom, though, we can create superpositions of two atoms together as well. Imagine we have two atoms, which we'll label A and B, each of which we apply a pi over 2 pulse to. Then the total state of our system can be described by the following four scenarios: 2-2, 2-5, 5-2, or 5-5. Or if we relabel our states to call 2-0 and 5-1, because it doesn't really matter what we call them, then we get 0-0, 0-1, 1-0, and 1-1. Our total quantum system now is in an equal superposition of all four states: 0-0, 0-1, 1-0, and 1-1. And this superposition works exactly the same way mathematically as our other one did. Changing the coefficients of each state changes the probability that each state gets measured. However, if we play around with different states, we find something interesting. If we just set up a normal superposition state with equal probabilities of all four states, measuring one atom doesn't tell us anything about the other atom. However, there are some states where this is very much not the case. For example, this is known as a Bell state. In the Bell state, there's a 50% weight to the 0-0 and 1-1 terms, but a 0% weight to the 1-0 and 0-1 terms. Now, if we prepare a Bell state and measure atom A to be 0, then we already know without measurement that atom B will also be 0. If we measure atom A to be 1, then we also know that atom B must be 1. This special superposition state that we've created is known as an entangled state, because the results of measuring one of our atoms tells us information about the other. If we want to generate this entangled state in the lab, however, it's not so easy. Regular superposition states that are not entangled don't require any interaction to generate, meaning that I can generate the states of atoms A and B separately. However, if I want to entangle atoms A and B, they must also be able to interact in some way. While electron spins and hydrogen atoms are great quantum systems to look at to understand the basics, the type of quantum computer that most people picture in their minds is made a bit differently. This is a superconducting quantum computer. These are the current frontrunners in the field of quantum computing. To understand how these work, we'll need to see how to apply the concepts of superposition and entanglement to electrical circuits rather than to atoms or electrons. First, though, we need some background information out of the way. Superconductors are a special class of metals which allow electrical current to flow with a zero electrical resistance. The current can literally flow forever. No, you cannot use this for infinite energy or perpetual motion, and yes, I'm sure. While I won't explain superconductivity in depth in this video, there is a quick visual explanation. Electrons are particles known as fermions. This means that they're a type of particle that likes to organize in a tower of states with one electron in each available state. However, if two fermions pair up, they can form a boson, and bosons can all occupy the same quantum state. When an electron moves through a crystal